I will introduce the method of implementing a univariate normal distribution from multiple regression coefficients. This presentation is based on our publication titled Simplified Methods for Modeling Dependent Parameters in Health Economic Evaluations, a tutorial. The SARS and R code for the examples can be found in the appendices of this article. I thank my co-authors. Regression analysis is a statistical method to estimate the relationship between a dependent variable and one or more independent or explanatory variables. We provided justification for the equivalence of using univariate normal distribution instead of generating a set of explanatory variables, such as age, sex, disease severity, for a regression model that includes a linear predictor. We also provided examples using parameters from a linear fixed effects model and a Cox proportional hazards regression model. This slide provided the details of the justification. We provided a summary in the next slide. One property of multivariate normal distribution is that the linear combination of multivariate normal distribution follows univariate normal distribution. See equation 9. Linear regression models, generalized linear models, and Cox proportional hazards models include the linear predictor of the outcome, given a set of values for the explanatory variables. We can assume that the estimated regression coefficients for linear predictors follow multivariate normal distribution. The values of these coefficients and the variance-covariance matrix can be obtained from the regression analysis. Let A1, A2, AP represent a set of values for the explanatory variables, such as patient's characteristics to capture heterogeneity. We are interested in knowing the distribution of linear predictor. We can directly calculate the mean and standard error of the linear predictor using the matrix products. Then, when we conduct probabilistic analysis, we can simply define the univariate normal distribution of the linear predictor to capture the patient's characteristics, instead of generating multivariate normal distribution data. Example 4. A United Kingdom study used a linear fixed effects model to evaluate the impact of diabetes complications on health utilities. The final EQ5D model included 12 explanatory variables. This article reported coefficients and the variance-covariance matrix of the linear fixed effects model in the main text and supplements, respectively. We defined a hypothetical patient with the values of these variables. We have summarized the steps of calculating the mean and standard error of the linear predictor via SARS-IML. Step 1. Import the coefficients and the variance-covariance matrix. Step 2. Input the values of the explanatory variables as a vector. And Step 3. Based on equation 9, calculate the mean utility value and the standard error of the linear predictor. Another property of multivariate normal distribution is a subset of multivariate normal distribution data also follows a multivariate normal distribution. We use the same method to obtain the distribution of the difference in utility between two hypothetical patients, given the differences in explanatory variables. When there is certainty about the order of utility values for two health states, for example, the utility value of one health state is always higher than the other, a gamma distribution can be defined to make the utility difference always positive. Example 5 was linear predictors in a Cox proportional hazard model. The Cox proportional hazard model includes a linear predictor. In the appendix of our article, we provided the details of the conventional method which generated the multivariate normal distribution data for the 5 coefficients to calculate log hazard ratio, and the new method to directly generate the univariate normal distribution of log hazard ratio. As showed in the plots, the distributions of hazard ratio of these two methods were same. Thank you.